Hi, welcome to EC&M Tech Talks. EC&M Tech Talks is a series of how-to videos where we cover everything from basic electrical theory to the types of equipment that we install and maintain out in the field, on through the various installation and maintenance codes and standards that we have that apply to this equipment. I'm Randy Barnett, and I'll be your facilitator for today's presentation on Ampacity. And these series of Tech Talk videos are brought to you by EC&M Magazine, Electrical Construction and Maintenance Magazine. What's important is that you go to ecmweb.com. That's ecmweb.com. And in the upper left-hand corner, you'll find a drop-down menu. So click on that. The very first thing you're going to find is something called Premium Content. You want to click on Premium Content and go to the Members Portal. Because when you get to the members portal, you can sign up. It's free, and you'll get tons of information on the various topics that we talk about on the Tech Talks, as well as lots of other information, webinars, and so on and so forth. You'll find that. So it's all at ecmweb.com and go to premium content. So, as I mentioned, we're going to talk about Ampacity today. And what is Ampacity? That might be the first thing we want to talk about then, huh? So Ampacity. Ampacity is how much current a conductor can carry under its conditions of use and not exceed the temperature rating of the conductor. It's its maximum operating temperature of the conductor. So let's talk a little bit about this more in detail. The copper, and coppers are probably our most common, right? We also have our AA8000 series, aluminum wire that we use, which is very good. But copper is probably our primary type of conductor that we actually use to carry electricity out in our premises wiring system. Now, there are three different types of conductor material then identified in the code. There's copper, and then there is the aluminum I mentioned, and then there's copper-clad aluminum, which is where they extrude a thin layer of copper over the aluminum when they manufacture it. Pluses and minuses for each type of conductor then. If you can go back to Chapter 9, Table 8 in the code. Chapter 9, Table 8 is going to give you the physical properties of our various types of conductors. It's going to tell you the dimensions of the conductors. For instance, all conductors 8 gauge and larger are required to be stranded per the code. This is stranded conductor. This is 2 AWG. And so it's required to be stranded. It is. And we can go back and look in the code, and it will tell in Chapter 9, Table 8 in the code, and it will tell us how many strands of wire we have, the physical dimensions of each strand, and the total overall dimensions of this copper conductor. Chapter 9, Table 8 doesn't address the insulation at all. One important thing to note back in Chapter 9, it also gives you the resistance in ohms of the conductor material per 1,000 feet. And so what you'll find is that the copper has quite a bit less resistance than a given length of aluminum does. So the result is, if I need to carry X amount of amps of current flow through a particular conductor, and I choose to use aluminum versus copper, I'm probably going to have to go up one size larger in my table. So in other words, maybe from a number 4 to a number 2 or something like that. So anyway, that's going to vary, but you can find all of those properties back in Chapter 9, Table 8 then. The insulation itself, depending on the type of insulation, has a lot different properties. For instance, this is a, THHN or THWN-2 insulation. So let's talk about this insulation. This is going to melt. This particular thermoplastic insulation will get soft and melt long before the copper conductor will. So the maximum operating temperature of the ampacity of the conductor is based on this conductor carrying full load for 3 hours or more, continuous rating then, and not exceeding the operating temperature limit on the insulation. Right? So we're going to find out in 310.16 is where we want to end up in the code to start talking about these ampacities. Now, we mentioned that the insulation material, this is a thermoplastic on this one. There are two primary types of insulation material that we use today. One is a PVC insulation, which gives us our thermoplastic insulations. The other type is a cross-linked polyethylene, XLPE. Probably the most important type of insulation, one of the most common anyway, that we get from our XLPE insulation is our Thermoset wiring insulation, Thermoset. The Thermoset insulation is usually designated by an R, which R used to be for rubber, right? But we don't use too much rubber insulation anymore. We use a Thermoset insulation. Now, what's unique about the Thermoset insulation is that it only melts one time. So in other words, in the manufacturing process, it is melted and applied to the wire. However, it doesn't melt again. So when we use our Thermoset insulations on our conductors, it doesn't melt again. Now, some of the disadvantages is the Thermoset's going to be quite a bit thicker on the thicker insulation over the conductor. In fact, if you take a look, you'll find in the code book we'll go to in a minute, but Thermoset insulations will usually be about 3 times as thick as the thermoplastic type insulations. So that's why one reason probably we don't use a lot of Thermoset if we don't have to. But it's got good properties to it. On the other hand, our thermoplastic insulations have a lot of good properties to them, even though the XLPE type insulations are a little bit tougher and stronger. The thermoplastics, very commonly used, fairly easy to pull through conduits and so forth. It's interesting too, you know, most of the insulation on a conductor is not there for insulation properties. Most of the thickness is being used for physical protection of the conductor. It doesn't take a lot of thickness of insulation to really give you, in this case, 600 volts of protection on this THHN. Now, the THHN manufactured from PVC then, it quite often has a nylon jacket on the outside of it. The nylon jacket does a couple of things for us. One, it gives some physical protection to the conductor material, which is very important because as we pull this conductor through our conduits and so forth, I don't want to nick the insulation certainly and thin it out or even expose any of the conductor material. So the nylon jacket gives me that physical protection. Depending on how the nylon is manufactured on our different types of conductors, is some very common tin AWG building wire then. So depending on how that nylon jacket is manufactured, it can also give us protection against oil or gasoline, or it can do both, depending, once again, oil and gasoline. So for instance, if I look on this building wire, typical building wire, it says 10 AWG, and it gives it in millimeters. It gives some UL numbers, MTW, machine tool wiring, which we can find in the code. Although we don't find the ampacity for MTW in the code, it says then RTHWN or THHN. So this conductor is either THWN or THHN. Well, which is it? Depends on our conditions of use we're going to talk about then. And it goes on, it gives it 600 volt class rating and nylon jacket, has a nylon jacket on it, okay? Quite often they will say oil and gas resistant as well, depending on the properties of the nylon jacket. If we take a look at probably one of the first places you want to go in your code book, then to start learning more about ampacity would be to go to table 310.4, table 310.4a, conductor applications and insulation rated 600 volts. So once again, I'm in the latest edition of our code book, the 2020 edition. Table 310.4a gives all those properties of that insulation that I was just talking about. And there's about 3 or 4 pages of them, so quite a bit to go through there. Probably one of the most important then is our thermoplastic type insulation, as we mentioned, like our THHN or THHW. So let's go through some of those designations and see what we can figure out. T. So the T indicates that it's a thermoplastic type insulation. We said an R would indicate a thermoset. An S would indicate a silicon type of insulation. Some of the thermosets and the silicons have some very good applications at higher temperatures. And so the T indicates thermoplastic. If it's, let's say it's THHN. If it's THHN, 1H means it's rated for 75 degrees C, the insulation is. The other H would mean that it's rated for 90 degrees C, and the N indicates a nylon jacket. If it's THWN, for example, these conductors all say THHN or THWN. Yep. Okay. And so that tells me that I can use it at 75 degrees C, which would be THWN, only 1H, 75 degrees C, if I'm using it in a wet location. However, if I'm using that conductor in a dry location, I can take it, or dry or damp location, I can take it all the way up to 90 degrees C. Okay, so that's the difference. And what does that mean? I can force more current flow through that conductor then to take it up to the higher operating temperature. As current passes through the conductor, there's resistance. The resistance produces heat. The more current flow I have, the more heat. The more heat, the more resistance. The more resistance, the more heat. The more resistance, the more heat, and so on. So for a given amount of current flow through my conductor, the hotter it's going to get. In fact, it's an I squared R loss. We take the amount of current squared and multiply it times the resistance. So in other words, it's not, if I double the current flow, I don't get twice as much heat. If I double the current flow, I get 4 times as much heat. So what's important to understand is that if I get a small increase in current flow, I can get significantly more heat being produced in my wire then. And I never want to exceed the temperature limitation of that insulation, be it 60 degrees C, 90 or 75 degrees C, or 90 degrees C, okay? And 90 degrees C is 194 Fahrenheit. Now, where do we find that information out? We have to go to table 310.16 in our code book. So if you don't have your code book handy, take notes so that you can go back and look this information up back in the code. And let's talk a little bit about table 310.16. In my 2020 edition of the code book, it's on page 161. Well, the title itself is important. Table 310.16, ampacities of insulated conductors with not more than 3 current-carrying conductors in the raceway, cable, or directly buried in the earth. Notes are always important on the table. Always read the notes. If I go down to note 1 at the bottom of table 310.16, it says ampacity correction factors must be applied where the ambient temperature is other than 30 degrees C, which it tells me is also 86 degrees Fahrenheit. So look at it this way. Let's get back to that definition we're going to talk about now on ampacities of conductors. Let's say I'm going to take some of this number 12 building wire, and I'm going to take and put it into a, in this case, maybe I've got some electrical metallic tubing. I put these conductors into the electrical metallic tubing. Now I start to pass some some current through them. And so the copper starts to heat up, which starts to heat up the insulation. I'm going to go to table 310.16, which is on page 161. And let's go down the 90 degree C column. So put a note in your notes if you're taking notes. Use the 90 degree C column for copper because we're using THHN insulation, which is found in the 90 degree C column. And go down until you find number 12 wire on the far left-hand side, 12 AWG. And you'll find that that number 12 has an ampacity rating of 30 amps. Okay? So this can safely carry in an ambient temperature of 86 degrees Fahrenheit and no more than 3 current-carrying conductors in a raceway. I can carry up to 30 amps of current flow through these conductors, and I will not exceed that 90 degrees C temperature insulation rating on the conductor insulation itself. But if I were to put more and more conductors inside of, well, maybe not this conduit, but something larger like the fiberglass or maybe some liquid type that I have or something like that, as I put more and more conductors in there, it just makes sense that it's going to be harder for the heat to escape from around those conductors. It's going to be warmer inside of a raceway when those conductors are carrying current flow. So what I need to do is I need to adjust for the number of conductors in my raceway. Well, that is table 310 15C1 has my adjustment factors for the number of conductors in a raceway. And it tells me, for instance, if I have 4 to 6 conductors in a raceway, I have to reduce the ampacity factor by 20%, or in other words, multiply that 30 amps that I had for these conductors by 0.8, 80%. And so 0.8 times 30 would give me 24 amps. So if I had more than 3 current carrying conductors in the raceway, it's going to get hotter in there. I can't allow these conductors to carry as much current flow. So even though their ampacity is 30 amps, their allowable ampacity based on the conductors in the raceway would be 24 amps. By the way, the green wire, is it a current carrying conductor? I hope not, should not be. So we don't count it when we do our ampacity calculations. Does it count for conductor fill? Absolutely. What about ambient temperature? Let's say I'm going to run these in a really hot area, through a boiler room or something like that, where the ambient temperature is going to be 100 degrees. If the ambient temperature is going to be 100 degrees, this was based on these properties for ampacity properties for these conductors were based on an ambient temperature of 86 degrees Fahrenheit. So I need to go back to another table and I need to correct for ambient temperature. So in this case, I go back in the code book to table 310.15B1, okay? And it's for correcting for ambient temperatures other than 86 degrees Fahrenheit, 30 degrees C. And so, for instance, if I look at 80 degrees, or excuse me, 100 degrees Fahrenheit is my ambient temperature, it tells me that my correction factor for 90 degrees C conductors would be 0.91. So now I have to take the 24 times 0.91 and gosh, what do you come up with on that one? You'll have to figure that out. About 91% of 24, right? So the amount of allowable ampacity in my conductors, good homework problem for you, right? So the amount of allowable ampacity decreases even more. Also, it matters whether I'm going to use this insulation in a dry, damp, or wet location. Dry, damp, or wet. So if I use this insulation in a wet location, they don't want me to carry it as much current flow as it will carry in a dry or a damp location. So on table 310.16, and why is that? Well, the insulation properties are going to change depending on the amount of moisture available around the insulation. For instance, actually the nylon jacket does absorb a fair amount of moisture. Anyway, so at 65 degrees C, or excuse me, I mean at 75 degrees C column, for using my conductor as a THWN, thermoplastic, 75 degrees C, 1H, and then N means nylon jacket. It tells me that the ampacity of this conductor now drops to 25 amps. So now if I were going to go back and do my adjustment and correction factors, I wouldn't be starting at 30 amps, I would be starting at 25 amps. So you could see I could end up with a lot lower allowable ampacity. Also, keep in mind 110.14c, it talks about that any chain is only as good as its weakest link, right? Even though this conductor may be rated for 90 degrees C in a dry location. If I heat this conductor up, if I pass that 30 amps of current flow and heat that conductor up to 90 degrees C and is connected to a terminal that's only rated to 60 degrees C, okay, what have I done? I'm going to overheat my terminal. I don't want to do that. So you need to refer back to 110.14 too when you're actually sizing conductors and determining ampacity values. Now, if I take a look back in the table, or excuse me, in the index in the back of the code book, I'll also find 10 different applications for ampacities in addition to 310.16. For instance, fire alarm systems, amusement parks, for example, solar photovoltaic, our PV systems, all have different ampacity requirements. The ampacity tables themselves go from 310.16 through 310.21. So 310.21, different types of conductors and materials, free air and so forth, different than 310.16. If you need to do ampacity calculations or find out ampacities for medium voltage conductors, you want to go to Article 311. The appropriate tables are in Article 311. Also, I should mention that you don't have to use the tables, right? These ampacity calculations can be done under engineering supervision as well. And that information is in the code. The bottom line is that we want to be able to do our calculations. We need to figure out how much current a particular conductor can carry without exceeding the maximum operating condition or the maximum operating temperature limit on that insulation. So we just said that ampacity is the maximum current that this conductor can carry continuously, meaning under full load for 3 hours or more, under its conditions of use and not exceed the operating temperature of the insulation. Now, what are those 3 conditions of use? We just talked about them. How many conductors I put inside of my raceway? That's one condition of use. Where am I going to locate it? Dry, damp, or wet location. That's another condition of use. And then the third condition of use, what's the ambient temperature? So that is all we've got for conductors today and ampacity. There are probably, you can, some good ways to do the calculations. Certainly get some practice. There's a lot of resources out there available to you. Go through and use the code book and make sure you know how to adjust and correct your ampacity values. And have a secret, get an app as well, right? Okay, apps can help you a lot. Even if you're working in the code and preparing for an exam, you can still use the app to check your answers, not in the test, but you can use them to check your answers when you're practicing for that exam, right? And it'll help you out. So anyway, that concludes our Tech Talk for today. Once again, this EC&M Tech Talk is brought to you by EC&M Magazine at ecmweb.com. It is part of the portfolio of the Endeavor Business Publications. And from now to the next Tech Talk, work safely.